exam. Final exam review. Yay. 2 moles of ideal gas undergo a reversible isothermal expansion at 220 degrees Celsius. During this process, 6,000 joules work is done by the gas. What is the change of entropy of the gas? Okay, delta U equal NCV delta T. Being isothermal, this means that this is equal to 0. Equals Q minus work. Therefore, the work is equal to Q, right? Yes. Is equal to N, let's see here, it's NR log, natural log specifically, I suppose the common log, of T final over T initial. Let me double check, make sure I got that right. I think that's correct. Work in RT. See, and it's V final V2. Nope, I did not do that right at all. So, give me my R. Try that again. Because this would be 0. Try that again. It is nRT, natural log of V final over V initial. There we go. That's better. Oh, we don't even care about that. It doesn't even matter. Because what it wants to know is what is change of entropy, which is equal to Q on T. Okay, that's really handy. Q, we are told by this equation here that work is equal to the change of by the heat flow is 600 joules, 6,000 joules, divided by the temperature, 227 plus the 227 Celsius plus the conversion of 317, bother me. Let's see if we can find it. There it is. 273.15 is 500. 500 Kelvin. Therefore, 6,000 divided by 500 is 12 joules per Kelvin. Okay. So it's not that, it's not that, it's not this, not that. Okay. Is it plus or minus? Change of entropy of the gas. Due to isothermal expansion, 227 Celsius expansion, that's an increase because there's more possibilities. So, one moment. So, entropy is a weird thing. Entropy is a thermodynamic count of the number of ways that a particular system can be counted that way. So, if you have two particles and you exchange them, that's the same situation. And so the question is, how many different ways can you get a volume of gas to have the same volume, temperature, and pressure? And that's related to what entropy is. So when somebody says that the entropy of the room increases when it gets messy, that's not entirely correct. The entropy, the room is, there's only one way that room could possibly be. However, the entropy of a messy room, of a room considered to be messy, is greater than the entropy of the room considered to be neat, because there are more ways for a room to be messy than for the room to be neat. And so that's that's actually more accurate to what we're talking about when we're talking about entropy. So when the gas expands, that increases the number of ways that the system could be in that state, because there's more volume for the system to fill. And so because there's more volume to fill, that means that there's more entropy to be had in that system. So now that means that the change of entropy must be positive for the increase in volume, which is more or less what we saw here which is what the signs say here. But the minus sign is just for those who aren't certain about their answer, shall we say. Carnot engines. A Carnot heat engine operates with between a high temperature of 800 Kelvin and a low temperature of 200 Kelvin. In each cycle, 400 joules of energy is rejected into the low temperature reservoir. How much work is performed by the engine in each cycle? Okay. Okay, so Carnot engines are the most efficient engine out there possible. And the reason for that is that they do not create entropy on they have, whoops, let me draw this out. So if we have on a PV diagram, we can have an adiabatic process, isothermal process, adiabatic process, isothermal process that returns to the star. So this adiabatic process here and here have a change of entropy of 0. Change of entropy of 0. This isothermal process here and this one here have the same are equal and opposite. And for going through the whole cycle means that the change of entropy for the system is equal to 0, and because of that makes this the most efficient possible engine out there, because it creates no entropy. As it turns out, hurricanes are well approximated by Carnot engines, are good approximations of Carnot engines. And so they don't increase entropy of the general universe. However, they do create a large amount of destruction outside of themselves on the ground, which would be an increase of entropy of the general universe. But that is not the hot reservoir or the cold reservoir. That is work being done. The destruction of a hurricane is work being done by the Carnot engine of the hurricane. But that means that these things make good questions because they are so efficient. Let's see here. Let's say So work, right? Heat? Nope. So Q cold is 400 joules, so we're told. And we're told that T hot is 800 Kelvin and T cold is 200 Kelvin. And it would like to know the work done by this thing. Let's see if we can get the right page. We can get the cold, we can get that there. Okay. So, D. And then the work goes there. Okay. So we need to take the ratio of these here. Nope, don't do that. So that means that that means that Q hot T hot, no, it was Q's, right? Q on Q, yeah. Q on Q is equal to T on T with a minus sign, because this is going to be negative because we're pulling heat out of the hot side. So Q hot is equal to QC T hot divided by T cold. So that's 8, but divided by 2 is 4 times the cold side. So that's a 4. That's 4 times 4 is 1600 joules. How much work is being performed? So subtract off the 400. Leaves us with 1200 joules of work being done. It's raining. Good for it. Alright, buoyancy. I'm not sure buoyancy was covered in this class. It's another one of those topics that tends to get the short end of the deal. But we'll do it anyways because it's not that hard to figure out. A block of metal with a density of 4 metric tons per cubic meter is suspended from a light string. When the block is in the air, the tension the tension is 39.2 newtons. What is the tension in the string when the block is totally immersed below the surface of the water that is in a bucket? The block is not touching the bucket. The density of water is 1 metric ton per cubic meter. Okay. What is tension here? Okay. So okay, there are ways to do this without figuring out what the mass is. But I think I'll go ahead and figure out the mass is because you'll also probably do it that way anyways. So we have 39.2 newtons divided by 9.8 meters per second squared will tell us that the mass is 39.2 over 9.8, which is probably well chosen. Yep, it is. 4 kilograms. Okay, so that means that that the water displaced, that it will displace water displaced is going to be 1 kilogram. So so that means that the mg pulling down is going to be 39.2, let's back it up, is equal to 39.2 newtons, but the water will have will be, buzz. Yeah, we'll get back to that. 7 Central. So let's see here. So okay, we have 39.2 newtons going down. Water displaced is 1 kilo, so it will be trying to push it back up with its own weight, with the weight displaced, so that the force of buoyancy is equal to the weight of water is equal to the weight of the displaced material. This is not a W, this is an M. This is mass. So that becomes 1 kilogram times 9.8 meters per second squared. That comes up to be 9.8 newtons. So now we can go that the buoyancy, so that means that tension is whatever is left over. So tension is equal to weight minus force buoyancy. So that is 39.2 newtons minus 9.8 newtons. And that works out to be 39.2 minus 9.8, 29.4 newtons. 29.4 newtons. There we go. 9.8 is the buoyancy force, and I don't know about the rest of that. All right, next page. A small rock is thrown straight upwards from the edge of the roof of a building with an initial speed of 16 meters per second. The speed of the rock just before it strikes the ground is 22 meters per second. What is the height of the building? All right, we are going to invoke energy conservation because that makes our life a whole lot easier. V squared is equal to V naught squared plus 2AD. We are looking for the height of the building? Yes. Therefore, D is equal to V squared minus V naught squared divided by 2G. 2A. We're going to leave it at A for now. Alright, final velocity is 22 meters per second, quantity squared, minus 16 meters per second, quantity squared, divided by, look at that, this is positive. Okay, so that means that we can go ahead and, yep, 2 and then 9.8 meters per second squared, end it, execute it. 22 minus, try that again, 22 squared minus 16 squared, end and divide by 2 times 9.8, execute, is 11.6. 11.6 meters. Second squared cancels with the second squared. This meter cancels with one of those meters on top, leaves a meter behind, 11.6 meters. Yeah, it's raining out there. Are you doing, what is it? Delivery? Bye then. A rock is thrown horizontally with an initial speed of 20 meters per second from a roof 16 meters tall of a building. What is the magnitude of the resulting velocity of the rock just before it strikes the ground? Again, energy conservation. So 1/2 mv squared is equal to 1/2 mv squared plus 2gh. No 2 here. 1/2 m. There we are. M's cancel, and multiply both sides by 2. V squared is equal to v naught squared plus 2gh. There we go. Velocity there, right? No, like, we want that one there. Okay. So v is equal to the square root of 20 meters per second squared plus 2 times 9.8 times 16 meters, 9.8 meters per second squared. Those units will work out. Square root of 20 squared, try again, 20 squared, plus 2 times 9.8 times 16, 26.7 meters per second. Alright. Next problem. A block with a mass of 6 kilos is on a horizontal surface. Coefficient of kinetic friction is this. There we go. Constant force of 50 newtons. Force directly applied at 53.1 degrees above the horizontal is applied to the block. A block slides on the surface. While a block is moving, what is the magnitude of friction that the surface exerts on a block? Alright. So this is a case where force of friction is not equal to mu mg cos theta, because force of friction is always equal to mu force normal, and there is an extra vertical force from the tension, which will reduce the requirements of the normal force. So I gotta watch out for that. All right, so we have an mg going down. We have normal going up. We have this one here, and so we're going to call that force y going up. And we don't care about the rest of that. So then we end up with, let's see here, normal minus 50, try that again, minus 50 newtons. And then we need the vertical, so that's a sine of 53.1 degrees, better known as 4/3. And then we add, all right, normal going up, oh no, these are both going up, and then we subtract off gravity going down. Gravity is 6 kilograms, 9.8 meters per second squared, and this is all equal to 0. Therefore, the normal force is equal to 6 times 9.8 minus 50 times 4/3 is, oh dear, interesting. Oh, I'm an idiot. Watch this. It's 4/5. Try that again, huh? There we go. That's a positive value, 18.8 newtons. Therefore, force of friction is 0.4 times 18.8 newtons. 7.52 newtons. I will wager that the wrong answer of mu mg is here. 0.4 times 6 times 9.8. Nope, it's not, surprisingly enough. Interesting. Not present. That is 23.52, which would be a none of the above. A small block is moving toward the top of the incline at 36.9 degrees. Above the horizontal coefficient of kinetic friction between the surface of the incline and the block is 1/2. What is the magnitude of acceleration of the moving block? Oh boy. Okay. So we have, I was going upwards, okay. So the forces acting on this thing, we have force of friction and the force of gravity parallel. So this is mu mg cosine theta. There is no other forces acting on this in the perpendicular direction, therefore we can immediately go straight to the default guess of mu mg cosine theta, and also add on to that mg sine theta for gravity. So here's our parallel gravity, and this is our force of friction. Okay, punch numbers in. Yeah? Yeah. Oh, you know what? This is equal to MA. Therefore, I can just immediately cancel out the M's. Leave me with A is equal to G mu cos theta plus sine theta. We know that these add together because the velocity is up the hill, which means the friction is down the hill, which is in the same direction as gravity itself. So now we can answer the question: what is the acceleration of the block? 9.8 times 1/2 times cosine of 36.9 degrees and plus sine 36.9 degrees. Huh. 9.8 meters per second squared. Is it really? I would like to verify that. So we have G here. So now I expect this to come out 1 if that works out the way I think it does. So mu is 1/2 cosine, this is the 4/5 plus this one here, and the sine is the smaller, right? Yeah. Yep. 3/5. So this is equal to g. 1/2 makes this a 2. So we have, yep, indeed, 2/5 plus 3/5 is indeed equal to g. Yep. That. How about that, humdinger? Keeping things simple like that. All right. Small rock. Mass 0.05 kilos. Attached to the lower end of the light string is 5 meters long. The other end of the string attached to the ceiling. Rock is released from rest string with the string horizontal, and rock moves in an arc of the circle. What is the tension of the string as the rock moves through its lowest point where the string goes vertical? All right. So this is 1/2 mv squared is equal to mgh, because we need to know the velocity at the bottom. Not really. We just need to know velocity squared. M's cancel, which means that v squared is equal to 2gh. Tension. So we're going to have tension going up and gravity coming down, and together they need to be my force centripetal. So that is equal to mv squared on r is equal to t minus, all right, yeah, mg. Therefore, t is equal to m v squared, 2gh, on r, which is h itself, h plus g. Therefore, h's cancel, and we end up with 3gh. M. Nope. Back up. 3mg. This looks awfully familiar. Like we did the same thing for a object sliding down a hemispherical bowl of some sort or another. Anyhows, anyhoosins. Tension is equal to 3 times 0.05 times 9.8. 1.47 newtons. 1.47 newtons. A small block with a mass of 0.2 kilos is placed against a horizontal spring attached to a wall. 2.5 joules of elastic potential stored in the spring. Spring is released from the block and then travels in the horizontal direction, leaving the spring behind. The coefficient of friction is 0.3. Speed of the block after it has traveled 2 meters. What is the speed of the block after it has traveled 2 meters from the point where the spring was released? Okay. What? Speed. Okay. So we have 2.5 joules available to us. Subtract off m. The force of friction is mu g mg. Try again. Mu mg is the force of friction, and then we need the distance that we traveled, and that is equal to, we'll find out later, or shortly, 2.5 joules minus 0.3, mass of 0.2, gravity, distance of 2 meters. That is 2.5 minus 0.3 times 0.2 times 9.8 times 2 is a positive value of 1.324 joules, equal to 1/2 mv squared. And V is equal to the square root of 2 kinetic energies divided by mass. Punch in our numbers. Square root of 2 ains divided by a mass of 0.2 kilos. 3.64 meters per second. In artificial satellite in orbit of the Earth, mass and radius is given. Circular orbit. In a circular orbit, if the orbit has a speed of 4,000 meters per second, what is the radius of the satellite's orbit measured from the center of the Earth? All right, I remember a similar problem. It was unfortunate that we were not given that equation for velocity, radiant velocity to radius. I believe it was down here somewhere. Let's see if we can find it and recycle our handiwork so we can save time. Nope, not in that bit. Here we are. V is equal to the square root of gm on r. All right. So what I found here is that the velocity is equal to 2 pi r divided by t, the period of the orbit. And the period of the orbit is given by 2 pi r to the 3 halves divided by the square root of gm. Move things around so we have velocity, and we find that v is equal to the square root of gm on r. Where is... Nope, not that one. This one. V is equal to the square root of gm on r. Okay, so we make it go back the other direction. So we need to square both sides and then solve for r? Yes. So we get v squared and then we trade. So r is equal to gm on v squared. Yes. I need G. It'll probably be on that one. Where is G? 6.67 times 10 to the minus 11. 6.67 times 10 to the minus 11. Mass of the Earth 5.97 times 10 to the... Oh, bugger. Keep hitting that. Oop, I was running out of space anyways. Whatever. We will go ahead and move it somewhere else. Shift B. N. R. Now we go for N. So that becomes N. There we go. 6.67 times 10 to the minus 11. Mass is 5.97 times 10 to the 24 divided by 4,000 squared. No funny units running around, so don't need to worry about that. 6.67 e minus 11 times 5.97 e 24 divided by 4,000 squared is 24887437.5 meters. 1, 2, 3, 4, 5, 6, 7. 2.49 times 10 to the 7 meters. 2.5. Take it. Next page. Energy conservation. T first. That is the right tempo now. Yay. Car A goes this way, 15 meters per second, 4 metric tons. Traveling due east, 50, yep. But they collide, stick together, yep. Road is icy, friction can be 0. What is the speed of the wreckage immediately after the collision? Alrighty. So, we're basically doing inelastic collisions twice. So we have that M initial, V initial is equal to M final, V final. So momentum is conserved. And we're going to do it in both directions. So we need that V final is equal to M initial over the total mass times the V initial. Okay, and then so for the for Vx final, we have 4,000 times 15 divided by 6,000 is 10 meters per second. Vy final is let's see here, 2,000 times 24 divided by 6 is 8. Okay, so this is let's see here, 4 and 5. That is unfortunate. So we go to our Pythagorean theorem. 10 squared plus 8 squared is, I don't know. That's why I have calculator. 12.8 meters per second. Look at that, exactly provided. Buzz buzz, I might need to know that. Okay. Yes, eventually. We will need to know that, but not yet. A hollow thin sphere has mass here, radius there, and moment inertia about the axis given by I is equal to 2/3 mr squared. The hollow sphere is released from rest at the top of incline, vertical height at 0.6 meters. If the sphere rolls without slipping, what is translational speed when it reaches the bottom of the incline? Conservation of energy. Energy initial is equal to energy final. So we start out with mgh is equal to our kinetic energy translation, 1/2 mv squared plus 1/2 I omega squared. 1/2 mv squared not equals plus 1/2 I is 2/3 m, same m, r squared. Converting omega to velocity becomes v on r squared. R's cancel, and we get 1/2 mv squared plus 1/3 mv squared. M's cancel. Be careful about that. Those m's because they don't always cancel. 1/3 plus 1/2 is 3, 4, 2/3. Right? No. It's a sixth. So it's 3 plus 2 is 5/6. So that comes out to be GH is equal to 5/6 V squared. V is equal to 6/5 GH under the root. Try it again. Well, it doesn't matter. Square root of 6/5 GH. 6/5 times G, 9.8, times our H of 0.6. 2.66 meters per second. These other ones are probably for the cases where people forget one or the other or both. And so if you're missing one or the other, then you have less inertia in your system, which means it can go faster. So that works out the way we expect it to. A large disk has a radius of 0.2 meters. It is mounted to a horizontal frictionless axis. Moment of inertia of the disk is given. Light rope wrapped around the disk and a block is suspended free from the rope, free end of the rope. System is released from rest. The block descends and the rope unwinds without slipping. As the block is moving, the tension is 16 newtons. What is the magnitude of the acceleration of the block? Okay. There are two ways to do this. This acceleration has to be related to the angular acceleration of this here by alpha is equal to a on r. So we could, in principle, just do that tension radius is equal to f, nope, that is fr, is equal to I alpha. Whatever. I alpha is equal to I a on r, and solve for a this way. So that would mean that t r squared divided by I is equal to a, and we find that to be tension is 16 newtons times the radius of 0.2 meters squared divided by moment of inertia of 0.16 is 4 meters per second squared. That would probably be the easy way to do that. What you are more likely to do is consider this thing here, where we have tension going up and gravity going down. So we have that mg minus t is equal to ma. Divide both sides by m, and we find that a is equal to g is equal to g minus t on m. Okay. Are we given the mass of the block? Oh, we are not given mass of the block. So, in fact, that is not the way to do that. That is interesting. But in principle, now that we have that this is equal to 4 meters per second squared, we could actually figure out what the mass of the block is. Well, I'm not doing that. But if we provide the mass of the block, then you could do this as well. So there's only one way to solve it, and it's the first way. How kind. That makes life nice. Alright, next page. Boink, boink, boink. First T. A wheel with a radius of 1/2 meters rotating with a constant angular speed of 3 revolutions per second. What is the linear speed of a point on the rim of the wheel? Alright, so they want V is equal to R omega. R is 1/2 meter. Omega is 3 revs per second. And you turn that into radians. So there are 2 pi radians per revolution. And that answer is, oh look at that, hold on a moment, real quick like. 1/2 cancels with the 2, so we have pi times 3, 3 pi, 9.42 meters per second. Revolutions cancel with revolutions, radians are unitless, meters per second. Ta-da! 9.42 meters per second. A uniform bar with a mass of 3 kilos is connected to the wall by a frictionless hinge. Light rope is connected to the other end of the wall. Bar is horizontal. Makes an unfavored angle. What is tension on the rope? Okay. So this is a torque problem. Torque is equal to 0 is equal to mgl over 2 minus TL sine theta. L's cancel to the other side. What are we looking for? Tension? Tension. So we end up with mg divided by 2 sine theta. M is, let's see here, 3 kilos. 9.8 divided by 2 sine of our 36.9 degrees. 9.8 divided by 2 times sine of 36.9 is 24.5 newtons. A block with mass of 1/4 kilo moves a horizontal friction surface. Block is attached to a spring. Spring constant provided. The other end spring attached to the wall. Spring pulled away and released. It has a simple motion, amplitude 0.4 meters. The maximum speed is how much? All right. So so we have 1/2 Ka squared is equal to 1/2 mv squared. Halves cancel. And we're looking for velocity. Velocity. V is equal to a square root of k on m. Alright. Amplitude 0.4 square root k 36 divided by a mass of 1/4. 36 is 9, a quarter comes up on top, 4 is 2, 2 times 9 is 18 times 4 is, I don't know, 4.8. Oh, right, well, 0.4, yeah. 4.8 meters per second. There's a standing wave on one wire that is stretched between two supports. Frequency is 80 hertz. Distance between adjacent nodes is 0.15 meters. What is the speed of the transverse wire? Okay, so looks something like this. And we're told the distance between adjacent nodes is 0.15 meters, which means lambda is equal to 0.3 meters. Once V is equal to F lambda, so that's 0.3 times 80. 0.3 times 80 is 24 meters per second. Yeah, it's pretty slow for a sound wave. It's probably not too bad for a mechanical wave of some kind or another. Last page. Two speakers, A and B, are driven by same amplifier emitting sounds that are in phase and have frequency of 85 hertz. Speed of sound divided. Point P is 6 meters from speaker A and 14 meters from speaker B. Is the interference at point P of the sound waves constructive or destructive? Okay. So let's see here, point A. So we have B here. Then we have A here. And then we have P here. We don't care about this interval here. We care about this one. And so that is 14 less 6. 14 less 6 is 8 meters here. Okay. What is the wavelength of this thing? So V is equal to F lambda. We're told F, therefore lambda is equal to V divided by F is equal to 340 divided by 85. And this should come out to be an integer of some kind or another. 340 over 85 is 4. Okay. So we have 4 lambdas between here and there. So an integer. So that's 1 lambda. And then I'll keep going. So another some number of integers. So that means that this should be effectively the same as constructive because they are in the same phase. Whatever's going on over here. A mass of ice that initially at 0 Celsius must be added to 4 kilograms of water initially at 80 Celsius if the final temp. What a mass? Okay. If the final temperature is be 20 Celsius. All right. Okay. So first we must melt the ice. Melt the ice. Raise its temperature by some amount, while adding to it some amount of water, which we're already told, by the same C and a different delta T, and all must be equal to 0. So we're decreasing the temperature of that same amount of water. So we end up with M, and then LF plus C delta T, there we go, is equal to minus M water C delta is T. So then we end up with mass that we are interested in is equal to, this minus will cancel that minus, so we end up with mass of water is 4 kilograms. Its C is 4190 not kilograms, joules per kilogram Kelvin, and it is coming down. This minus sign will cancel with the minus sign of the minus 60 Kelvin. Kelvin cancels Kelvin, kilogram cancels kilogram, divided by LF is here, not on that page. Do LF 334 times 10 to the 5. 334 times 10 to the 5 joules per kilogram plus 4190 joules per kilogram Kelvin, coming up 20 Celsius, or Kelvin. Kelvin cancels Kelvin, kilograms stays there. Inverse joules under joules cancels, and so this inverse kilogram comes up on top as a kilogram. Mass is TBD 4. Clear that. 4. 4190. 60 divide 3.34 E5 plus 4190 times 20. End and execute. 2.41 kilograms. Last question. A quantity of monatomic ideal gas undergoes a process in which 60 joules of heat enters the gas, and the gas expands and does 90 joules of work. In the process, both the pressure and volume gas change. In this process, does the temperature increase or decrease? Okay, so delta U is equal to NCV delta T is equal to Q minus W is equal to Q coming in, right? Expands, yep, Q coming in, enters, yep, Q coming in, 60 joules. Does work, and work leaving of 90 joules. This is minus, minus 30 joules, which indicates a delta T which is less than 0. So now, I would say it decreases the temperature. And let me double check, make sure that I have not screwed that up. Previous exams. No, don't do that. Don't do that. I would like to double check my handiwork without that. Open a new window. No, don't do that. Don't do that. Don't do that. Oh, here we go. There we go. This is exam final for 20 with the answers. Preview. Do the end. Ta-da! Correct. I indeed got that correct. Yay! Just making sure that the signs go the way I think they do. All right. That is the last question of final exam for 2020.